Hello, everybody. This is the lecture for section 4.5, derivatives and the shape of a graph. So like I said in previous sections, right, chapter 4 deals with the application of the derivative, right? And specifically, we've been building up slowly and slowly, bit by bit, up to basically uh, trying to determine what a graph is actually doing or what a function is actually doing without being actually able to graph it. Okay, so that's what we're going to be doing here today. We're going to be studying how the derivative sort of influences the shape of a graph. Okay, and all we need really is that idea of sort of slope of a tangent line or the instantaneous rate of change. Okay, a lot of this, as you guys can sort of surmise, can be double checked using Desmos or some other graphing utility, just so that you can sort of verify your thought process, make sure that you're doing it right, okay? So the first thing I wanna do is I wanna go ahead and describe the first derivative test. So some of this stuff we've already sort of picked up already, right? This is just going to be the very first time I'm sort of formally introducing it to you. So the first derivative test, let me put that up a little bit, there you go, only needs only two things, right? Just the derivative of the graph and whether or not, the derivative of the graph and whether or not it's positive or negative, okay? So if a graph is increasing over an interval AB, right, then the derivative is going to be greater than 0 for all the values in there. So, right, let's go ahead and do an XY graph, right? So here's an X, here's my Y. I'm going to draw in a graph, and I hope it's not, yeah, it is. It's going to be super thick. There we go. So it doesn't matter how it's increasing, right? So let's say both of these are our functions, right? You can tell that the derivatives for them, right, or the slopes of the tangent lines, they're all going to be positive. So and therefore they're increasing, right? Okay. And likewise, right, if a graph of a function is decreasing over an interval, right, then we have this. That derivative is going to be less than 0. So same idea. Here's an X and a Y. Here's my XY. I'm going to draw some decreasing graphs. It doesn't matter how it's decreasing. Let's say it's decreasing this way here or this way here. It doesn't matter, right? All of these slopes of tangent lines here, they're all negative. They are all sort of dropping, right? Okay. That's the only idea that we need. Okay. So that was sort of like a little bit of the concept behind it, right? Here's the actual first derivative test. Okay. Suppose that you have a continuous function over an interval I equal AB, okay, containing a critical point C. Okay. If f of x is differentiable, right, then you can satisfy one of these three things. One of these three things right here, okay? If the derivative changes from positive before a critical value to negative after a critical value, right, then you have a maximum. Right? And if f prime changes from negative to positive after the critical point, right, then you have a minimum. Okay, and then the very last one, if the sign of the derivative is the same before or after, then you have neither. You have sort of what we call is, you'll learn this in Calc 3, a little saddle point. Okay, it's sort of like climbs, sort of stops climbing. There's a little saddle. It just sits there for a little while and then starts climbing in, or vice versa. Okay, so the drawing for this, right? So let's say we had the maximum one, right? So let's say that we had a graph that did this, right? We know that this has a maximum, right? So you guys can see before the critical point, right? All those slopes are positive, right? And after the critical point, all of those slopes are negative, right? And I should have drawn an X and a Y here, X and Y. So I'm talking about this value right here. So this is our critical value C, okay? And then likewise, if we do the minimum, right? There's an X, there's a Y. If you have a minimum, then the graph does this, right? It dips and then goes back up. We know that this point right here is our minimum. That point right there is our critical value, C, right? Whoa, what happened there? It somehow magically zoomed in when I didn't want it to. There we go. Right? So then notice what happens at the minimum. The slopes before are negative, right? And the slopes after are positive. Okay. So notice all we use there is the idea of the slope of a tangent line, right? The slopes of the tangent line before versus the slopes of the tangent line after. Okay. This is a pretty good problem-solving strategy for determining what kind of maximum or minima or what kind of extrema you have. Okay. Step one, right? Find the critical values. Okay. And divide the interval into smaller intervals using the critical values as endpoints. I'm going to show you guys what that means. You're basically divvying up, you're divvying up sort of like the number line, but it's based off of the critical values, okay? Number two is analyze f prime in each of the subintervals that you made from step one, okay? And then step three is use the first derivative test to determine whether you have a local max or a local min or neither. Okay, so to show you guys how this works out, I'm going to leave both of them there. So I'm going to use the first derivative test, right, to find the location of all extrema for that function right there. Okay, I'm going to use the graphing utility afterwards to verify my answer. All right, so the first thing I'm going to do is I'm going to go ahead and find all the critical values. So that means I need to find the derivative. Okay, so I'm going to need to find the derivative of this thing right here. Okay, and the derivative of that thing is going to be, that's a product rule. So f prime of x is going to be the derivative of the first, right? So 2x times e to the x times the second plus the first x squared times the derivative of the second. The derivative of e to the x is itself. This is going to be the section of the class where reducing anything will be helpful for you so that you don't have to do too much mental math, too much sort of algebraic manipulation, okay? So let's go ahead and reduce this a little bit. If you guys can see, there's an e to the x in both of these, so e to the x, and what gets left behind is 2x plus x squared, okay? This is great because now we have this thing right here. This is a little bit more we can factor it a little more. It's going to be e to the x times 2 plus x, 2 plus x, right? So critical values, right? Is when f prime of x is equal to 0, right? So then therefore, that means e to the x times 2 plus x must equal 0. This tells us, right, e to the x can never be equal to 0. It's an exponential, so that's always going to be positive. But then this one can be 0, so x can be 0, or x has to be equal to -2. Okay? Okay. So we have our critical values. We did number one. We did part one. So part one, find the critical values. Actually, we're not done yet with part one. We need to now divide the interval, right? In this case, no interval is given, so I'm going to use all real numbers. I'm going to use the critical values to divide up all real numbers into smaller intervals, and we'll analyze the derivative on each one for step two. Okay, so what do I mean by that? Here's my number line, and I'm actually going to move it over a little bit. I have room to label some stuff. Okay, scroll down a little bit. Okay, my critical values are 0 and -2. So I'm going to do 0 here, -2 here. Okay, so these are my critical values. So I'm going to put here on the left-hand side here, I'm going to put to denote that I'm doing critical values, right? So I'm going to divide up the x-axis, right? I'm going to divide up all real numbers into these intervals right here. There's going to be from -infinity to -2, -2 to 0, and then from 0 to positive infinity. Okay. Okay. So now I'm going to go ahead and choose representative values within each one of these smaller intervals. So I'm going to choose for over here, I'm going to choose -3. Over here, I'm going to choose -1. And over here, I'm going to choose 1. Okay. Now, was there a rhyme or reason to these numbers? No. I could have just as easily chosen -1.5 to substitute for -1. The only reason I didn't is because I think -1 is going to provide us with a little bit nicer, nicer mental math, if that makes sense, right? So choose your values so it's easy for you to compute them out. Choose your values, okay, to compute them out. Okay, so we have our sort of representative values. So I have my number line created here, okay? And what I'm going to do is I'm going to plug in these representative values into the derivative, okay? And we're going to analyze the sign of the derivative at those values, okay? So what I'm going to do is I'm going to do f prime of x. I'm going to rewrite that here. So it's going to be x e to the x 2 plus x, right? So now I'm going to go ahead and plug in my value -3 into this derivative. So it's going to be -3 e to the -3, 2 minus 3. And if we take a look here, -3 e to the -3 and the -1. So this looks like it's going to be 3 over e cubed. Okay. Now, remember what I said. I don't care about what value this is in particular. I care about the signs. Okay. This tells me that it's positive. So all of the slopes in this interval are going to be positive. Okay. Let's go on to the next one. I get to plug in -1. So -1 e to the -1 times 2 minus 1 minus 1 e to the -1. That's going to be times 1. -1 over e. We take a look at that. That value is negative. That value is negative. Okay. Now let's go ahead and do the very last one. 1 e to the 1 times 2 plus 1 in this case, right? This would be 1 e to the 1 times 3. So this is going to be equal to 3e. I don't care about the value. I care about the sign. That is a positive value. Okay. So now, let me actually write what we were doing here. This is step 1, right? This right here is going to be step 2 from our list from above here. So the last step is use first derivative test to determine what kind of a local extremity you have, right? So here's step 3, very last bit. Okay. Step 3 says, look at your signs and determine what kind of extrema you have, right? So the first one I'm going to look at is this one right here at -2. Okay. At -2, the slopes before are positive and the slopes after are negative. Okay. So according to the first derivative test, right, this means we have a maximum. So okay. And then likewise now, if we do x equals 0, our second for our second critical value, the slopes before are negative and the slopes after are positive. Okay, that means we have a minimum. And that is it. So notice I didn't really have to graph this. This is how this kind of this is how the first derivative test works. It tells you if you have a maximum or minimum. That's it. Okay. What comes up next here is a quick check. Thankfully, it's only odds and evens. Try to do this without graphing it. Obviously, you can go ahead and graph it afterward, but really, really try to do it without sort of graphing it first. Okay. Okay. The next thing we're going to get into is concavity and points of inflection. Okay. This really has to do with more the second derivative than the first derivative, though we're going to throw in the first derivative here and there when we get to the second derivative test. Okay. So the first thing I want to go through is this definition. Okay. Let's say you have a function that is differentiable over an open interval AB. Okay. If f is increasing over I, right, we say that it's concave up. Okay. And if it's decreasing over I, we say it's concave down. Okay. And we're talking about f prime here. So that means the slopes of the tangent lines are increasing. Okay. So let's go ahead and see what this means really, right? So if a function is increasing, if f prime is increasing, that means that the slopes of the tangent lines are increasing. So that means this is going on, right? So if you guys notice, right, the slope here is low, but it gets higher and higher and higher as we go up, right? Does that make sense? So f prime is increasing. The slopes of the tangent lines are increasing, okay? Notice what happens on this side over here, right? That it's bowling up, right? Since it's bowling up, we say this is concave up. That's basically all it's saying. Okay. If f prime is decreasing, okay, this one's a little trickier one to do. F prime decreasing means that it is concave down. So I'm going to go ahead and do one of these, right? Okay. Let me move that back into the middle. There we go. So notice what's happening to these. Slope is really steep, but the slopes become less steep as you move along. Does that make sense? So f prime here is decreasing. Does that make sense? The slopes are getting less and less steep, okay? And notice what's happening to our graph, our blue line, right? it's bowling down, right? So then this means it is concave down. Okay. That's it. That's all it is. That's all it is. Just interpreting slopes of tangent lines. Okay. So now let's get into a couple more hard-hitting facts here. This gives us two pretty important things here. The first one is the test for concavity. Okay. Let f be a function that is twice differentiable over ab. Okay. That means if the second derivative is greater than 0 for all x and I, then you have f is concave over I. And if the second derivative is less than 0, then f is concave down over I. Okay? Does that make sense? So let me go ahead and do the two, well, let me go ahead and do the same thing, right? That, if we have one of these, right? So this is concave down. That at every point here, let me draw an x and y here. That's what I forgot to do. Aha. X and y, right? That if you choose any point here, right, then the slopes of the tangent lines around those points are getting lower and lower, aka the second derivative is going to be negative. So then you have something that's concave down. Okay, and then likewise, you do an x and a y. You have something that's right. Choose any point. And if you take a look at the derivatives there, right? They are very steep negative, but soften up. The slopes of the tangent lines are increasing, right? So then this one is going to be concave up, and this one is the concave down. Let me label this right here. Yeah. Okay. The next definition that I want to sort of explain here is that of an inflection point. Okay. The inflection point is when the concavity of your function changes. Okay. So if you take a look at all of the functions that we've been playing around with here in class, they can do whatever they want. They can squiggle up, they can squiggle down. As you guys know what the definitions are now, they can concave up and concave down, right? There comes a point, a real nice point, where it goes from bowling up to bowling down, right? It goes from concave up to concave down, or vice versa. It goes from concave down to concave up. That point is called an inflection point. So the best way to describe it, right, is if it goes like this. So this is concave up, right? And it switches to a concave down like this, right? This point right here, right, is the inflection point. Or the other way around, right? If it is doing the opposite, it does this, and then it switches to something like this, right? Both of these points, both of these purple points are the inflection points. Okay. The way that you would find an inflection point is that you set the second derivative equal to 0. Thank goodness, it's as simple as that. So a critical point is when the first derivative is equal to 0. The second derivative equal to 0 is the inflection point. Okay. Okay. This brings us all down to the very last theorem of the class, at least for this section, the second derivative test. Unfortunately, this one works a little backwards, okay? And I'll explain what that means in a second, okay? Suppose that x equals c is a critical value, okay? Suppose x equals c is a critical point of f, and f double prime, the second derivative, is continuous over an interval containing that value c, okay? If the derivative is greater than 0, then you have a local minimum. Okay, notice how these work a little backwards, right? If f double prime is less than 0, if it's negative, right, then you have a local maximum. Okay. If you have that it's equal to 0, then the test is inconclusive. You can't give me anything, right? And this goes, so the idea behind this, right? I'm going to go ahead and do minimum here and maximum here. The idea of this is just looking at how the slope of the tangent lines are behaving. That's basically it, right? So let's go ahead and do an x and a y again. X and y, you make it an x. Okay. So let's say, right, you have a graph. Let me do, this one has to be a minimum, right? So let's do this, right? And let's say this is our critical value right here. So this is our, this right here is our value c, right? Notice that the slopes before are negative, right? And the slopes after are positive, right? So then that means the slopes of the tangent lines are increasing, okay? Notice what I said. The slopes of the tangent lines are increasing. Therefore, the second derivative must be greater than 0. Okay? Let's go ahead and look at the other one. I'm going to do an x and a y. So just FYI for everybody that's listening right now, my mailman should be coming by any second now, and my dog will go completely ape crazy. So don't get scared. Okay, same idea. Here's our value c. We said that this is a critical value, right? Notice what's happening here. The slopes before, as we saw before, right, are positive, and the slopes after are negative, right? So the slopes of the tangent lines are starting positive and turning negative, right? That means the slopes of the tangent lines are decreasing, right? The slopes of the tangent lines are decreasing, aka f double prime is less than 0. Therefore, you must have a local maximum. Okay. And that is it. Okay. So let me go ahead and do this very last example. This one's going to take a really long time. Okay. It's going to take up a fair amount of space here. And I think, yeah, I'm not sure that is. Quick check. Okay, so let's go ahead and use the first and second derivative test to graph this thing, okay? And the test for concavity to see if we can sketch it, okay? Now, in terms of drawing this thing out, I'm not gonna make it too big of a deal of how this thing is gonna look. You don't have to give me exact points, so long as you sketch it somehow and provide a little bit of context, sort of justification from your math, that's gonna be enough, okay? So the first thing I'm going to do is I'm going to take the derivative of this function right here. I'm going to take the derivative of this function right here. Okay, so I'm going to go ahead and do that. Let me first get my notes out. Yeah, okay. So I'm going to be skipping a fair amount of steps here. I do expect you guys to reduce the answer. I will give you the reduced form, okay? So just make sure that, you know, when you're doing the math, when you're doing the algebra, you get it down to this point, okay? So the first thing I'm gonna do, like I said, is take the derivative. So f prime of x, I'm gonna go ahead and start doing the derivative of this. So it's gonna be below, right? I'm gonna put parentheses around it, x squared minus 2x plus 2 times d high, so it's gonna be 2 times x minus 2 times 1, which is the derivative of the inside, minus high, x minus 2 quantity squared times d low, which is going to be 2x minus 2 all over the bottom squared. So x squared minus 2x plus 2 squared. Okay. This right here should factor down to, I'm going to give you guys the cleaned up version. Okay. 2x squared minus 4x all over x squared minus 2x plus 2 squared. Okay, here's my derivative right here. So I sort of reduced it as far as I could. This is, you should get something either this or similar. Okay, so now I'm going to do first derivative test. Okay, first derivative test. Okay, I need the critical values, right? So if I want critical values, f prime of x has to be equal to 0. So therefore, this thing, 2x squared minus 4x all over x squared minus 2x plus 2 has to equal 0. I'm going to use the fact that I sort of showed you guys from a previous section. If you have a fraction that's equal to 0, right, the only way that that can be equal to 0 is if the top is equal to 0. So 2x squared minus 4x has to be equal to 0. Okay, thankfully this factors. So it's going to be 2x x minus 2. Right? So this tells us that either x is equal to 0, right? Or x is equal to positive 2. We have our two derivatives. So now I'm going to scroll down a little bit. I'm going to do my number line. Okay, so this is going to be my 0. This is going to be my 2. I need to choose my representative values, right? So negative 1, 1, 3. I'm choosing these values just because they are the nicer, and I forgot the square here. I think I might have erased there. These are nice values, so you can do the math with. That is it. Okay, so I'm going to rewrite over here f prime. I'm going to rewrite it nicer a little bit. So 2x, sorry, x minus 2 over minus 2x plus 2 squared, right? Let me grab that, move it. Need to pick it up and chuck it over here a little bit more. There we go, so I can get a little bit more space. And it didn't take the price. All right, so I'm going to go ahead and start plugging in values here, right? So if I plug in negative 1 into this thing, I'm going to get 2 times negative 1 times minus 1 minus 2. That's going to be minus 3 all over minus 1 squared. That's 1 minus 2 times minus 1, that's minus positive 2. That's going to be positive 2 plus 1. That's going to be 5 squared, right? So this is going to be something along the lines of negative 6, positive 6. So 6 over 5 squared. I'm going to actually do this again. I'm going to grab this. I'm going to sort of just chuck it over a little bit, just so I can have a little bit more room to play around with here. So 6 over 5 squared. This is a positive value, so positive. Okay. Do the same thing with 1. So it's going to be 2 times 1, 1 minus 2, all over 1 squared minus 2 times 1 plus 2 squared. I know I'm taking a lot of pauses here. Check your arithmetic. Usually this is where people mess up, and this is it gets annoying. It gets annoying. 2 times 1 is 2. 1 minus 2 is a minus 1, so I'm going to get here 2 times 1, that's 2 times a minus 1 here, all over 1 minus 2 plus 2, so it's going to be 1 here, squared. Like I said, I don't care about the value, really. Let me do that as a 1 squared for real. There we go. I don't care about the value here, really. That value is going to be negative. All I care about is the sign. Okay. Next one, let's go ahead and do 3. So it's going to be 2 times 3 times 3 minus 2. So it's going to be 1 all over 3 squared minus 2 times 3 plus 2 squared. 2 times 3 is 6. 9 minus 6, that's 3 plus 2 is 5 squared. So this is going to be another 6. I'm going to write it to the right of it. 6 over 5 squared. Positive. Okay. So what we have here, right? So last step right here is, since it's going from positives to negatives here, we have a maximum at x equals 0. And then since it's going from negatives to positives, okay, this is going to be a minimum at x equals 2. Okay. Okay. That concludes first derivative test. Okay. So let me go ahead and do second derivative test. So the second derivative test deals with whether or not we have local maximums or minimums, right? So it turns out that if we grab the second derivative, okay, we grab the second derivative and they're positive or negative, they tell us whether we have local maximum or minimum. We already know that we have local maximum or minimum from the first derivative test, right? So this should basically verify what we're trying to look for from the second derivative or the first derivative test, right? So let's go ahead and do the second derivative test. Okay, so let's go ahead and do f double prime. We need f double prime, right? Which means we need to take the derivative of the first prime. Yeah, you see how long this gets? This one right up here. Okay, So I'm going to write it out, and I'm going to give you guys a nice simplified version. Okay. So low x squared minus 2x plus 2 squared times d high 4x minus 4 minus high 2x squared minus 4x. Write that in for real. Times d low. Here's the fun stuff. 2x squared minus 2x plus 2 times the derivative of the inside, which is 2x minus 2, all over the bottom squared. So it's going to be x squared minus 2x plus 2. It's squared, and then I gotta square it again. Therefore, this is now to the 4th. Okay. If you simplify this, I'm going to at least do that. I highly suggest you go through the math and the arithmetic to reduce this down to something very nice and pretty. If you do so, okay, you should get something along the lines of this. Minus 4x minus 4 times x squared minus 2x minus 2 all over the bottom, x squared minus 2x plus 2 cubed. You should be able to grab this, all of this, and reduce it down to this, okay? Or some version of it, okay? If you can't get exactly here, I wouldn't stress too much over it, okay? Just, eventually try to get down the algebra. It's going to be required that you show the algebra steps at least to a certain extent, okay? Try your best to reduce it down to that very final line, okay? So now, what I'm going to do is I'm going to take the second derivative, right? And I'm going to plug in my my critical values. I know what the critical values are. It's 0 and 2. Right? So f double prime of 0, right? It goes into right here. So minus 4 times 0 minus 4, 0 squared minus 2x minus 2, or minus 2 times 0, sorry. Minus 2 all over 0 squared minus 2 times 0 plus 3 cubed. I get here 4 minus 2 over 3 cubed, right? And this, if you can tell, what's this less than? It's less than 0. This is a negative value. So then therefore, remember how the second derivative test works, right? It goes backwards. If this is less than 0, right, then that means you have a maximum, right? So now f double prime of 2, let's go ahead and do this one really quick. Negative 4, 2 minus 4, 2 squared minus 2 times 2 minus 2. Oh, so many 2s. 2 squared minus 2 times 2 plus 3 cubed. There we go. Okay. 8 minus 4 is 4. So this is going to be a negative 4. This is going to be 0 minus 2, so it's going to be minus 2. All over 3 cubed. And this is bigger than 0. So remember how second derivative tests worked. Bigger than 0 means you have a minimum. So that sort of verified these two facts right here. We already had them, but it gives us sort of that information again, right? Okay. The last thing I want to do is the test for concavity. Okay. So I'm going to do that over here. I'm running out of space here. Test for concavity. Okay. So remember how the test for concavity worked. Okay. It's that if we plug in a value, and if it's positive, right, we knew that is concave up. And if it's negative, we knew that it is concave down. Okay. So inflection points, that's the thing that we need to find first. So inflection points, right, that means that f double prime of x has to be equal to 0. Okay. That means this right here. I need to set this right here equal to 0. Okay. I'm going to allow you guys to do that on your own. I do expect you guys to try that out. Okay. I will give you guys the inflection points themselves. So the inflection points, right, are at x equal 1 plus or minus the square root of 3. You'll use the same logic that we did for the stuff from above. Okay. So now the question is, how do I use these points? I'm going to go ahead and do the number line again. Okay. And I'm running out of space. Okay. So we have these three values right here, these two values right here, right? These are the inflection points that we found out, right? I get to plug in these values. Well, first of all, let me go ahead and choose representative values. So I'm going to choose something nice. I'm going to choose, let's say, -1 here. Okay. The reason why I put 0 here is to differentiate, to give this thing a space. I know this value is negative. So I'm going to choose my representative value between these two as 0. Okay. And then I'm going to choose a point up here. Let's call that point up here. Let's say we choose value 3. Okay. And since I ran out of room, I'm going to go ahead and scooch this over here. I sat on this hoping that I gave myself enough room, and I ended up not giving myself enough room. So I'm going to go ahead and do f double prime of -1. Okay. So I'm going to write it up here so we don't forget what it is. F double prime of x is equal to minus 4x minus 4 times x squared minus 2x minus 2 all over x squared minus 2x plus 2 cubed. Okay. So if I do f double prime of -1, okay, then I'm going to go ahead and plug it into here. So minus 4 minus 1, oops, minus 4. And then I'm going to do minus 1 squared minus 2 minus 1 minus 2. I hope I don't mess up again. Minus 1 squared minus 2 minus 1 plus 2 cubed. Okay. If we reduce this, go ahead and reduce it. Let me move the equal sign a little farther down. Okay. This is going to be a minus 4 minus, that's going to be minus 4 minus 4 is going to be minus 8. 1 plus 2 minus 2 is going to be 1 all over. Plus 2 plus 2, that's going to be 4, plus 1 is 5. 8 over 5 cubed, right? This is bigger than 0. So according to our test for concavity, right? Everything before this, let me actually leave it there. This is telling us this is concave. Whoops, wrong color. Since it's positive, it is concave up. Okay. F double prime of 0, the next point that we're going to use. Okay. This is going to tell us, let me go down a little bit, F double prime of 0. Okay. This is going to tell us, let's go ahead and plug it in one more time. Negative 4, 0, minus 4, 0 squared minus 2 times 0, minus 2, all over 0 squared minus 2 times 0 plus 2 quantity squared. There's going to be a minus and minus 4, so it's going to be positive 4 minus 2 all over 4. So we have something that is less than 0. So then we know here that this, between these two values, it is going to be concave down since it is negative. So we have something that looks like this here, right? So I'm going to leave this last one for you guys to try out. F double prime of 3. You should get that this is bigger than 0, right? So then this is going to be concave up. Okay. Now, let me zoom out a little bit so we can get everything in the shot here. Here we go. Now we need to sketch this thing. Okay. There's a lot of information here. Okay. I'm going to let you guys sort of figure out how to divide up your X and Y axis. Okay. It's up to you to decide how you want to sort of divvy them out. I'm going to go ahead and do 2 squares is going to be 1. So this is going to be 1, 2, 3. Okay. It's up to you guys. You can leave them as 1, 2, 3, 4, 5, right? But I'm going to do 2 just so we can get as big a space as possible, right? Okay. So I now need to incorporate all of this information into my graph. Okay, so we know at 0, there is a maximum. At 0, there's a maximum. So I'm going to go ahead and start popping points here. At 0, here's my 0. There's a maximum. It's going to be up here somewhere. I don't know what the value is. If we wanted to know the value of it, we can easily go ahead and plug it in. But like I said, this is just a rough sketch. Okay. At 2, there's going to be a minimum. So 1, 2. Maybe I'm going to say it's right there. I'm not going to make it too fancy, right? Okay. The slopes before 0, they are positive. So they are somehow increasing. So maybe something like that, maybe, right? Let me actually make them a little bit more. Okay. The slopes afterward, between 0 and 2, they're negative, they're dropping. So they're going down like this, right? And then the slopes after 2, they are positive. So they've got to be increasing. I'm thinking something like this. Actually, let me do this. I'm going to go ahead and do, right? Okay. So that took care of what we got for the first derivative test. You guys see that? It satisfies all the stuff from the first derivative test. That's this thing right here, right? And the second derivative test already told us where the maximums and minimums were going to be. We already got those pretty nicely, right? We know that since f double prime of 0 is negative, we have a maximum. And at x equal 2, the double prime of that is going to be positive. So therefore, we have a minimum, right? Okay. So now the next thing we have to do is just double check the, and look at me go. I didn't highlight the, okay. We have to make sure that the test for concavity matches up. Okay. So notice that what we have here is legit, right? It satisfies everything that we need already. So before the square root of -3, or 1 plus the square root of -3, it is concave up, right? Between the two values, it's got to be concave down. So this is actually not exactly there, right? So let's go ahead and find these 2 points right here. 1 minus the square root of -3 is, that's about 2 point something. So that's going to be about right here. Okay. And then 1 plus the square root of 3, that's going to be 2 point something. So that looks like it's going to be somewhere over here. Okay. So what this actually means is our blue graph is not entirely correct. Our concavities don't match up entirely. So what this graph actually should be doing is it increases right here. Here's where the concavity changes, okay? Which means that it's going to start to bowl. You see how that bowling's happening? So over here, it's concave up like this. Afterwards, it's concave down. Okay, so that's what I mean about the bowling. Okay, from here, it's going to be concave down to our minimum, right? And then it should bowl up afterwards. Like that. Okay. I think we got it all. Okay. The next thing that's up. Hopefully these aren't as hard as the one that I made you do. There's the mailman. Bronx, 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 Bronx. Stop. Perfect timing. Huh? Okay. Next thing that's up is quick checks. Go ahead and try to do the exact same thing that I was doing. Keep your thoughts in order. Like I said, I don't really mind if the values aren't there. Just give it a rough sketch. Use the information that's from first derivative test, second derivative test, and the test for concavity to try to fit everything in as best as possible. Give me a rough sketch. Doesn't have to be entirely exact. Okay. And then after that is lecture questions. Okay. If there's any questions about this stuff at all, this is going to be a really heavy section. This is going to be a lot of stuff. Okay, a lot of spots where you can mess up. Okay, come by my office hours, come by my drop-in times, or just send me an email. Okay, if there's any questions, hit at me, get at me. Okay. Besides that, I'll see you guys around.